Presented by Caltech.
And this is, I guess, an interesting contrast with some of the other ones that we've seen today where, Yisung asked me to talk about AI in relationship to sustainability and energy and issues like that. And the way, at least, we've been using machine learning AI tools in our group in that context is not the kind of static inference question that we've heard a lot about in some of the previous talks. It's a much more dynamic, adaptive use where you're trying to learn or optimize in a dynamically changing environment, and that's where the challenge comes from. It's not about learning a static concept once and being done with your archive in the sky. It's about learning and adapting in an environment that's constantly changing. And so that's kind of, I think, an interesting contrast compared to some of the talks we've seen today. So the motivation for this stream of work that I'll tell you a little bit about and give you a vignette into today is that renewable energy isn't coming anymore, it's here. So there's lots of great illustrations of this. This is, I think, a very compelling one. It may be hard to see the numbers in the back, but we're pushing 20% of generation in the US coming from renewables these days. It's growing quickly still, despite the administration priorities that we have today. Still growth is happening. And you can see this, not just are we growing in what is being installed, but across the US now there's renewable standards and goals that are being set and legislated in a large number of states. So the dark green have legislated ones, the light green have voluntary, the gray states have not yet instituted renewable portfolio standards. But the interesting thing is these are long-term goals, but 15 states already have 100% clean energy standards that have been legislated. And so kind of the starting point for this work and for a large part of what's going on in the Resnick Institute these days is this feasible at all? Like, is this a silly thing to legislate at this point, or can we actually, what needs to be accomplished in order to get to 100% clean energy in our system? And basically the perspective that's happening in Annenberg and the group that's looking at smart grid is the what if question, where suppose we do have cheap wind, we have cheap solar, all of those technological advances happen. Are we done? And basically the answer is no. There's still a lot to do, even if you have those advances that happen, because even when you have a lot of wind and a lot of solar and they're cheaply installed and they're everywhere, they're not so easy to integrate into the system. There are system questions about how to manage and operate the power system in the grid that you need to solve, and learning and adaptive environments and these sorts of questions are really crucial to those things. So to highlight where those challenges are coming from, I'd say there's two easy to understand issues that come about. The first is wind and solar are variable, and we all know this. Here's an illustration of this. All the individual colored lines are profiles of generation at the same location, different days in a month. And so you can see, wind, there's a nice steady average, but there's no day that's steady, and there's no predictability and there's huge variability across days as to what's coming. Solar, again, there's a nice steady, predictable average, but the variation per day is very hard to predict and depends on clouds and all of these other things, and you can have extreme drops and rises depending on what happens in the world around you. And this is a challenge because if you're going to operate a system like the grid, you need supply to match demand at every instant, at every time, in every location. And with input like this on the supply side and demands that is hard to predict as well, how do you make these match at all points, at all times? And the way is you don't actually end up being able to use all the renewable energy that you are producing. So because of this variability, curtailment is common, just turning off there's wind generation or there's solar, but you don't input into the grid because it's more than you predicted and you can't make use of it. And also backup dirty conventional generation is really important, because suppose you've predicted that the sun will be out, a cloud goes over, something happens to your solar panels, dust comes on them, a dust storm, wind, fire, smoke, whatever. Now all of a sudden you have to ramp up generation from conventional sources very quickly, and the generation that you can ramp up quickly is the dirtiest conventional generation. And so actually there are lots of illustrations where you install a huge amount of wind, you install a huge amount of solar, and yet your emissions go up because of the responses created by things like this. Germany had this at a large scale as they were first installing renewable energy, for example. So that's one. That's the one that maybe everybody sees and has heard of. The second one that hopefully you've heard of, but maybe you haven't, is in addition to the variability and the volatility and the unpredictability, they change what the net demand profile looks like. So if you think of the energy that we use as the demand, the net demand is that minus the renewables. And here's a very famous picture of what renewables are doing to our net demand. So the 2002 line is up top, and you see as more and more solar, this is California on a day in March. So you see that peak where there's sun out, that valley where there's sun out is getting deeper and deeper. And this is called a camel becoming a duck, because in 2012, you basically had a camel there as what the profile looked like, and these days it looks like a duck. So this is called the duckbill curve today. And why is this problematic? Well, one thing is it means that valley is deeper. That means conventional generation, which can't react quickly, like nuclear, which is very clean in terms of emissions, just can't make up as much of your energy portfolio. And that forces you to use generation that can react more quickly, which is often dirtier, to counter that. So less baseload is a bad thing for sustainability. It forces steeper ramping when the sun goes down and everybody's going home, and so power is rising already, but the sun is going away, so you go from a lower valley to a higher peak. That's really bad. There's very few forms of generation that can ramp quickly, coal being the primary one that's often used. And so again, this means more dirty generation. And then shorter, higher peaks. Again, this is a problem because you end up using more of the peaker generators, which tend to be dirtier. And so all of this increases the need for dirty generation or curtailing renewables, because if you just don't let the renewables be used into the grid, then you can mitigate all of these issues. And this is a real thing. So this is a plot showing how much curtailment we're seeing already in terms of solar and wind in California. And you can see that as the solar penetration level gets up to 10, 12, 20%, you're having a lot of curtailment for economic reasons, for cheapness reasons, and some for security already happening. And once we start to get anywhere near significant penetration from wind and solar, all of a sudden you're throwing a lot away. You're throwing 20, 25, 30% of it away just because of operational constraints in the way things are run currently. So that was your quick tutorial on, is it feasible? Well, even if we have cheap wind and solar, it's not clear how we do this well. There's a hard research challenge to be addressed. And this is what we've been doing in our group with Stephen and many others, Stephen Lowe and many others at Caltech. And basically the answer is you need new markets. You need to redesign the way markets work for these. You need better control policies for the operations. And maybe the biggest thing is you need adaptive distributed energy resources around the grid. And so if you want to hear about markets, that's a different talk. That's not AI, but I'm giving a talk on that in the Sizzle Center in a couple weeks. So let me know if you want to do that. So I'll talk about the DERs today. And so these are things like electric vehicles charging their load, but you can charge them at different times in the day. You can schedule when you charge them. They're adaptive potentially. Storage, wall battery, like the Tesla wall battery being a good example. If you have storage resources around, you can make use of them in different ways. A smart thermostat is something that, again, can interact in an adaptive way with the grid. Pool pumps are one that's undervalued, but is a huge resource in terms of adaptive energy. You don't need to use your pool pump at particular parts of the day. It can happen whenever you want, and they use a significant amount of energy when they're running. And then one that I did a lot of work on in our group, data centers, just to give you an example of another extreme size, right? These don't have to be small little devices in your home, because these can be big smart buildings, data centers, factories, even things like a Walmart store, where they adapt depending on what's going on in the environment to provide resources for the grid to use. And so that's the really fundamental thing. You have all this potential from sources like that, if you can make use of it, you can avoid the issues that we saw, for example, with the duckbill curve, where if you have variability, you can use those resources to adapt and respond and smooth out that variability. If you have an oversupply because your base load is too high at the bottom, you can use those, you can turn on all the pools, you can use that moment to run air conditioners, things like this, charge electric vehicles. You can reduce the ramping rates by scheduling when these things happen, and you can avoid shortfalls at the top by deferring loads that may want to be run then to different points later in the evening. And so it gives you a way to manage all of those challenges that we saw in the previous slide. But of course, doing this is hard. And there's a lot of reasons why it's hard, from designing markets to getting a decentralized market to coordinate in some way to react to these. But at the core, sort of underneath all of those, is an ML problem, which is that what you need to do with these DERs is you need to balance their usage, their demand, with the supply, the renewables, the net demand that's available, or the net load that's out there. And you need to do this in a situation where you don't know what's coming in terms of renewables. Predicting accurately, even at a small scale, is hard if you're thinking of responding to these. So that's a place where kind of static machine learning and AI is useful. But the bigger thing is switching an action is costly. And so to give you an example of what I mean by that is, if you think of adjusting the thermostat in a house, this happened to my house. I have a personal experience with this. If your Nest adjusts it too quickly or too often in response to signals, the air conditioner is going to break. And so we ended up having to replace many parts of our air conditioner because of too quick adapting by the grid to these sorts of things. And that costs thousands of dollars for a consumer if that happens, right? And so issues related to changing too quickly is bad, not just from an inefficiency standpoint in terms of heating and cooling, and an uncomfortable standpoint in terms of the people in the room, but it can break the material and cost significant money, or break the machine and cost significant dollars. In terms of electric vehicle charging, the same issue, right? So you can imagine charging, discharging, using an electric vehicle as part of the grid, but if this drops the lifetime of the battery in your car by 50% or 2/3, that's really bad. People aren't going to be able to do that. The cost of that is too significant. And then at the large scale data centers where we started with our work, if you're swapping a server into and out of deep power saving modes, the wear and tear costs of that are basically on the order of running the server for 2 or 3 hours. So you better be able to leave that server off for at least 2 or 3 hours, preferably 2x, 3x that, if you're going to be able to have any cost savings or benefit from doing this sort of dynamic adaptation. So that, combined with the fact that predicting what's going to happen in the future is hard, makes this a really challenging online learning problem, because you need to figure out what you're going to do in terms of your action now. That's going to incur some costs now, but you don't know whether it's worth it to incur that cost because you don't know what's going to happen in the future. Okay? So that's kind of formalized in what's called online optimization in machine learning, or AI. And the version of it that's relevant for these problems is smooth online convex optimization, because you want your actions that you're choosing over time to be smooth. And so I'm an algorithms person, so you're going to see equations and theorems and things like that. I don't like to give talks without those. So, but I'll start with a cartoon. And so what is this problem? Well, this problem is, there's some set of actions. This is, the configuration, the choices you're going to make in your system to control your DER. You're at some place currently, x0. Then there's some cost function that arrives. This is, trying to match the renewables. If you don't match them perfectly, there will be some cost from being either too much or too little in terms of how the grid responds. So you're going to choose a new action to try to optimize that cost. It's called a hitting cost that you incur on that function. But then you also incur a switching cost, or a movement cost, that is keeping you from changing too often, too quick, or too far, too quickly, too often. So you pay both for the cost function that you incur because of the situation at that time, and for how much you change your action over time. That's the fundamental thing. This happens over and over again. You get a new cost function, you make a new choice, et cetera, et cetera. And unfortunately, it looks like the light grays aren't showing up, but the old ones are supposed to be there. And this example was chosen because here you move around a lot back and forth, but in doing that, you're always tracking the minimizer with the choices that I showed you in that animation. If you had just moved once to X1 and stayed there, you would have been better off. rather than kind of tracking the individual choices along the way. And you can see that because this is kind of a flat cost function. You didn't really need to go all the way out to x2 for the x2 one, and so on and so forth. So it would have been better to just kind of move once and stay steady, but you couldn't know to do that without knowing the cost functions that were coming in the future. And so that's the fundamental challenge here, is how do you decide whether it's worth it to incur the cost to switch if you don't know the future, right? So this is an adaptive online learning problem here, because you're trying to learn the best action profile without knowing the future, but you incur this cost to change, and that's why it's called smooth. So here it is in math in terms of the offline problem. And for those who aren't in CS, often this kind of problem is evaluated in terms of what's called the competitive ratio, where what you're trying to do is you're trying to match the performance of the best that anybody could have done if they had known what was going to happen. So the offline optimal that's in the denominator there is the cost that if you knew exactly the sequence of cost functions that were going to come and you just solved that problem, you would make this set of actions. You hope that with online choices without knowing the future, you can do nearly as well as that. And nearly as well means keep that ratio to be a constant, and you want as small a constant as possible. Okay, and so you're comparing against the offline optimal. Now, like I said, I'll go over this quickly, but we got interested in this because of sustainable data centers, and we basically asked the same problem that you want to ask at a societal level at the data center level first, which is, could you run a data center on entirely renewable sources? And the same problems of, you need to be able to adapt the usage of computers, you need of the servers through right-sizing the capacity, on and off in power-saving modes. You need to be able to defer workloads depending on whether their deadlines will allow it so that you can run them when renewables are available. You need to have a kind of tool that's a combination of that. That fits in exactly this model. Your X of t, your action, is the states of each of the servers. You have constraints on the workloads that depend on when they can be run. So you have some box constraints on the workloads that fall into that optimization problem. And the renewable availability and the cost of delay shows up in that cost function. And so you can write this down. In this problem, we worked with HP and Google kind of over a year to get the right parameters for this problem. And the cartoon of what you want to do is you want to take a workload that looks like this. This was a real workload at an HP data center, and turn it into something that looks like that. Of course, you can't really do that because workloads can't be run whenever you want them to be run, but that's sort of the goal. And the challenge is exactly what I said. You don't know the future. You can predict it with some noise, but you don't know it precisely, and switching is costly. So if you move when you shouldn't, that's a big problem. And so, we actually took some of the algorithms that I'll tell you and deployed them, at a real industry data center in Silicon Valley, and it works, right? So you can use these tools to reduce energy usage. In this case, we reduced industry usage over a month by 80% from the grid, and there's now some products out that use the algorithms from this kind of research. So, beyond data sensors, this model is now a really common thing in energy. So the top-tier energy conferences have a session or two each year that are looking at algorithms and improvements for algorithms in this space for lots of different specific applications. Here, there's a huge number. And then it's not just in energy that this stuff is relevant. I borrowed some of Yisung's pictures, even though the model is a little different that he uses, but he's my host, so I'll use him. But you can use the same idea when you think about animation, robotic camera planing, because if you think of the robotic planing example, if you have a camera that you're controlling in an autonomous way to video, say, a basketball game, you want to keep the ball in the center of the screen. But you can't just move it to follow the ball precisely. You need to move it in a smooth way, otherwise the quality is awful. And so you again have a cost function, which is kind of where the ball is in the screen, and a smoothing cost, which is keeping you from being really jerky in how you control the camera. Facial animation, the same sort of thing. If the lips move in a really jerky way, that's really bad, but you need them to be in certain positions for certain sounds that are going along with the audio. One that I've been involved in is video streaming. So there's now standards that are being deployed by Akamai and others around video streaming that really take SOCO, this type of model, as the basis for how to control the smoothness here, of course, in the videos that you're streaming, with the quality of the video being the cost function. So there's a lot of others as well, but those are three that are really compelling and deployed in real situations. And this, on the math side, has led to tons of variations. So if you think of the problem that I showed you, you can have lots of different versions of constraints, lots of different properties for your cost functions, lots of different forms of switching costs, depending on what you're looking at. For control people in the audience, if you take the switching cost to be the L2 squared, then this can be really directly reduced to LQR control. And so you can go back and forth, and you can get results for LQR control with the algorithms that I'll preside here. OK, so good. I wasn't sure how long that part would take. I have plenty of time for some algorithms. So the rest of the talk, I'll get into some of the actual algorithms. So how do you, without just the motivation for why we care about problems like this, how do you actually think about designing algorithms for problems like this? And so I'll end with a new one that we really like. And so to do this, I'll switch into teacher mode a little bit. So if you take learning or online algorithms course, there's basically a couple set algorithms, which are the first ones you always start with thinking about when you approach a new problem. And to sort of show you why those techniques don't work, I actually only need a very simple setting. So think of a setting now where there's only two cost functions in the environment. They're both linear. One is decreasing, one is increasing. And you don't know which ones you're going to get when. So what do? Well, the first thing you learn in an algorithms class is that greedy algorithms work really well a lot of the time. And so let's start with that. So suppose you just have a greedy algorithm. What does that mean here? It means if you're given cost function 1, you choose action 1. If you're given cost function 2, you choose action 0. Nice and easy. But now what if the environment gives you an alternate set of cost functions where one is very steep and one is very shallow? Greedy is kind of silly, right? Greedy is going to do 1, and then 0, and then 1, and then 0. So it's going to switch every time to the minimizer, which means every time it's incurring a movement cost of 1. So if you do this t times, then you'll incur cost t. Whereas the optimal thing to do would just be to always stick at 1. You don't pay very much here, but you avoid moving. Then you get the optimal. You're not optimal, but you don't pay very much because that's not very shallow. And so then your cost is, each time step you pay less than 1 over t, either 0 or 1 over t, so your cost is less than 1. So you're giving up an order of magnitude better, 1 versus the length of the time horizon when you compare the optimal and the greedy. And that really highlights kind of one point about these algorithms where you have to really consider whether it's worth it to switch. If you're just switching because it's better, you're going to make big mistakes, and you're going to be way off from what the optimal could do. OK, second attempt. The next thing in learning these days, gradient descent, right? So here we don't have to do stochastic gradient descent. We just do gradient descent because we know the problem. Seems to work everywhere, right? So does it work here? What does that mean here? It means you kind of just decrease, take a small step downhill, depending on which cost function you get. OK, so suppose we start out with C2. We're starting out somewhere. We're kind of walking down. At some point, the environment starts to give you C1. And so then you walk down there. And so what is the environment making you do? The environment is going to basically make you, in the worst case, just always walk on the upper envelope of the cost functions. That's pretty bad. So in some sense, you'll settle down at the bottom of that V, which is not terrible, because if you settle down at the bottom of that V, if you had to choose one action to always play every time, the static optimal, you've found it. And so in a static environment, gradient descent works well. But in a dynamic environment, suppose these are both steep functions, you should never be playing in the middle. You should always be playing on one of the ends. And if you're always playing on one of the ends, that's what the offline optimal would do. That would be way better than something like gradient descent that's going to settle down at that static point. And so in a dynamic environment, learning the best static point is a terrible thing to do. Right? That's the punchline here from this little example. OK, so given that, neither of the basic sort of day one algorithms work, what can you do? Can you do better than this? Does this just mean it's too hard to match the performance of the offline optimal? So this is where we started in our group. This problem has been looked at for maybe 30, 40 years, but it was about 10, 15 years ago, or I guess, what is it? Yeah, a little 10 years ago or so is when we started, and in 13 we first had our first result here, which was, in retrospect, a very basic result, a toy result. So it says, let's look at the one-dimensional version of the problem. All the pictures I've drawn are one dimension. So let's just look at the one-dimensional version and see what we can do. In the one-dimensional version, you can do really well, surprisingly. And this was the first time that there was any sort of constant bound on an algorithm in this one-dimensional world. And it was a pretty small constant, 3. You can always be within a 3 of the optimal with an algorithm that we called lazy capacity provisioning. And I start with this one because it has some nice intuition, and it'll give you some intuition about thinking about these problems. So the way lazy capacity provisioning works is you define 2 bounds. Don't worry about how yet. And then the algorithm is lazy between those bounds. So it always stays between those bounds, and if it doesn't have to move, it doesn't. So it keeps the same action unless one of the bounds forces it to change its action because it has to change its action to stay between the bounds. And so it kind of goes up. Here it's forced to move because the lower bound is going up. Here it can just stay constant, but then all of a sudden it runs into the upper bound, so it has to stay in it, so it has to move down and follow it. So that's the algorithm. That's why it works that way. And the bounds, don't worry too much. They look almost like the offline problem, but they're only solved up to that time period. The key difference is that you pay cost only to move up in one and only to move down in the other. So why does this work? Well, it works because we can prove that the optimal has the same structure, except instead of going forward in time, it's going backwards in time. And so you could really characterize what the optimal looked like. And you could also, by characterizing the optimal, show why you can't do this, why you can't be optimal with an online algorithm. Because to know that you should drop off of the upper bound here, you would have to be able to compute what this bound was going forward, but you don't have the information to be able to compute that. So it's going to be impossible to match the optimal online. But you can mimic the structure of it in this way, and by mimicking the structure of it, even though you're kind of shifted a little off, you're doing very well. Okay, so that was our starting point. It was the beginning. It's not the best algorithm for the one-dimensional case. You can take that 3 and with a lot more complexity make it a 2. And so there's been maybe 5 to 10 papers pushing that in the one-dimensional case. But then basically this opened up a lot of questions about how to do other types of constraints, how to have battery constraints, or if you can use predictions to help yourself do better, lots and lots of other things. And there's been hundreds of papers written in the years since on pushing variations of this just in the one-dimensional space. But basically the big open question that none of that was able to address, which we finally were able to address this year, is can you do well beyond the one-dimensional case? So the world isn't one-dimensional. You need to be really high-dimensional. If you think of the data center, there's hundreds of different types of servers, thousands of different types of workloads. So the product of those is the dimensionality that you're working with when you're designing something in that space. And so how do you do well in the high-dimensional case? And as a quick diversion, for a long time, and this is kind of a good illustration of how computer scientists think, the way to make progress, the way we thought we could make progress on this was to look at what is a seemingly simpler problem and show that that seemingly simpler problem is actually equivalent to the one that I showed you so far. And so the seemingly simpler problem is convex body chasing. Which is exactly what its name says. So now instead of worrying about there being cost functions, all I'm going to do at each step is give you a body. And at every step, all you have to do is be inside the body. So you're always going to move to somewhere inside the body. And the only cost you pay is the cost, the distance of the step you take. And so every step you do, you move in, every step you do. So this is simpler, right? Because I don't have to worry about optimizing a function. I just have to worry about getting into the body. The question is just where in the body I should be. And clearly, it's really hard to know that without knowing the future. So if you know the future, you could sort of figure out where you want to be in the bodies. But without knowing the future, it's hard to know where you should land in the body, whether it's worth it to go to the far side of the body or not. So it's a seemingly simple problem. Kind of surprisingly, you can prove that it's equivalent. So any algorithm for SOCO can be used to solve this. Any algorithm for this can be used to solve SOCO. So it's completely equivalent. The only difference is you need to go up or down one dimension between the problems. And so there's a long time where people, this is a problem that dates back to the 90s, like online convex optimization, but it's been looked at by a lot of people in recent years, including some of the really big names in machine learning, like Sebastian Bubeck. And a lot of progress has been made, kind of culminating in, I put this paper up because it's kind of a one that's easy to poke fun at in terms of theoretical computer science. So this was a breakthrough result this year that published that showed that finally there was an online algorithm that worked for this problem, that you could get a constant factor. It's just that that constant factor was 2 to the 30d. And notice that I said there exists an online algorithm because they didn't exhibit the algorithm. They showed that there did exist. You could prove an existence argument for an algorithm that had this, wonderful guarantee, right? And so this was, 10 years of progress to get there. Luckily, things got better soon after. So, within a month after the conference, there were 2 other papers that brought that 2 to the 30d down to d log t. So that's a big improvement. But we proved a lower bound of root d. And so it's impossible for this problem to get down to a constant factor of the optimal. You're always going to pay something that grows in the dimension and grows reasonably quickly. Not absurdly quickly, but in the square root of the dimension. And so kind of, this put an end, at least in terms of making progress on online optimization through convex body chasing. It's still an interesting problem in its own right. And so we went back to the drawing board, and you started to realize that meant you had to impose some sort of properties on the cost functions if you were going to do well for the algorithmic problem in this space. And so what could you impose that could let you do well? And so this year with Gotham, one of the students in our group, so we were able to prove that you could do well as long as you had strongly convex cost functions. So you couldn't handle that linear case. It turns out that toy example that I showed you that seemed so simple, the linear problems are the hardest. But if you force yourself to have some curvature, then you can do well. And you can do well in a lot of contexts. So I'm putting one particular result. We have a bunch of results here with a bunch of other grad students as well. But this one is nice because it includes these squared L2 switching costs. So for the control people I see in the back, this means that you have a provable competitive ratio worst case guarantee for what is typically approached in a very stochastic randomized way, which is quite nice. Okay, and the key thing about this theorem, ignore the math and whether you know what big O means or anything. The key thing is there's nothing here that depends on the dimension of the problem. So it's a constant that's independent of how high a dimension you look at the problem in. Right, and so the interesting thing is what's the algorithm? So the algorithm, we call it online balanced descent. And here's the picture illustration. So suppose you have a point here. These circles are the level sets of the function in some very high dimensional space. Via t is the minimizer of the cost function there. Okay? And now, what would you do if this were gradient descent or mirror descent or something like that? You'd move in a perpendicular direction to the level set where you are. Okay, so that's kind of standard machine learning know-how. But think of what would happen if you did that and you landed on this level set. Now, all of a sudden, given that we care about how far we moved, we could have just gone there, had the same cost, but moved less. And so that says that instead of moving orthogonally to the level set where we are, instead of paying attention to the geometry locally where you are, you should be paying attention to the geometry where you land. And that's one of the first key insights in this algorithm is you need to pay attention to the intermediate geometry, not just the geometry where you're stepping off when you're doing these sorts of optimization. And the second thing is you need to select the level set where you're going to land. And in gradient descent, all you're doing is you're taking these small step sizes and gradually converging to the static optimal. Here, when you want to pay attention to how far you're moving and you want to move to track a dynamic environment, you need to really decide how far you're willing to go. And then once you've decided what level set you want to land on, you just project onto it so that you're taking advantage of the intermediate geometry. And so this really pays attention to not just the local geometry, but the whole geometry of the function. And that's kind of the key insight that underlies the algorithm. So in math, this is what it is. This level set that you're choosing is one that should balance the hitting cost and the movement cost, and it balances it in a linear way. So linear, so this is the hitting cost, L is the cost at the level set, this is the movement cost, so you really want to balance that. And then you project onto that. So that's the algorithm. That's OBD. Now, this was a big breakthrough, but I haven't said anything about whether it's optimal. Could you do better? So we worked on that a bit, and unfortunately, the answer is it's not an optimal guarantee. So your dependence here is on 1 over m. M being small is the hardest case. M being small is closest to linear. So The lower bound we can show is like 1 over square root of m, so that's better when m gets small. And so you could ask whether this gap is, OBD could be suboptimal, or it could just be that our analysis wasn't good enough. Turns out it's that OBD is suboptimal. OBD is never going to be better than m to the 2/3. And in proving that, we actually get a really nice intuition about what's wrong with this algorithm. And so I'll show that in the picture here. So what's wrong with the algorithm is you need to not just pay attention to the intermediate geometry, because if you just pay attention to the intermediate geometry, this minimizer could be moving away from you without affecting the intermediate geometry. So you need to additionally pay attention to kind of where that offline optimal could be, which is near this minimizer, and make sure that you're not letting the minimizer run away from you as the environment changes. And so to make sure that the minimizer can't run away from you, a simple thing that you could say is just after I do this projection, take, again, a balanced step, but ignore the geometry and just move in the direction of the minimizer with that balanced step. And now what you do with this greedy version of balanced descent is you combine those, and so the step you're making is the combination of that projection plus a little greedy step. Okay, and so that's the idea. You can make it even simpler. So rather than paying attention to all these geometry and projections, you can actually write this just as a convex minimizer, convex problem that you're solving in each step. And so if I had more time, I'd explain why this is equivalent. It's not too hard to see. But that's now the version. So this now, the greedy, the sort of step towards the minimizer is enforced by a regularizer out here. And so this is called regularized online balanced descent. And this is both computationally easier and, amazingly, it is precisely optimal. So not just does it get close to the optimal that you could hope to do from an online algorithm, but we can prove that it gets exactly up to every constant the performance that's the best you could possibly get for an online algorithm in this setting. Now, the restriction here is we're strongly convex and specifically L2 squared switching costs. So you can ask, can you extend this to broader sets of functions for the mathematically minded people in the audience? There's a lot more work to do here. But it's really, we nailed this problem after 10 plus years of us working and 30 plus years of the community working. And so, coming back to this question, you can really, you can get beyond one dimension, and you can get beyond it optimally. I'll kind of stop there and just say, this is a nice culmination of a lot of work here. We've made huge progress over the last decade on these sorts of problems, but there's still a lot to do. So we've had huge progress on the algorithmic side, lots of big successes in actually deploying these algorithms to data centers, to EV charging, to video streaming, to microgrids, even to content distribution networks with Akamai. But there's a lot of open questions. I haven't talked anything about here the fact that, yes, you don't have predictions in these energy systems. You don't have perfect predictions in these energy systems, but you do have predictions. It's not like we have no idea what's going to happen with the wind or the sun. And so you should clearly be using that in these algorithms. And so there's a whole stream of work about how to use predictions of future that are noisy in algorithms like this to improve on the results that I've shown you. And so there's a lot of nice things to be said there. And one of the nice things is, OBD's work. Gotham is now in the back if you want to ask him about it. So this is new, right? This is just in the last year. And so there's a whole opportunity now to revisit these applications with what is a more powerful algorithm at this point. So we're excited to do that. And as a teaser for those of you here who like non-convex problems, we just submitted on Monday a version of this where we can get provable near-optimal guarantees for cases where the hitting cost is instead of convex, non-convex as well. So with that, I'll stop. Thank you. Yeah.
So I have a very mathematical question.
Good.
So I can see that you need strong convexity to be dimension-free because the balanced descent may not be feasible if it's not strongly convex, because there may be degenerate dimensions where you just can't find that.
We get dimension-free and non-convex too.
I see. So, but how do you? Okay, I'm thinking of like if the cost function was like L1, you may be the case where the balanced step is you just can't find it.
So the key thing is not convexity for that. It's an alignment or an order of growth bound that connects the hitting cost and the movement cost. So you need the growth of the hitting costs to grow linearly, or at least the way we've proven it, linearly in the sort of norm or whatever you're thinking of the movement costs as being part of. And so L2 is the right parallel to strong convexity.
You always find that stuff.
Yeah,
It's not some degenerate geometry.
that's right. That's right. Yeah.
So, okay, I have a second question.
Yeah.
Conceptual. So of course you have features, we have features of what kind of jobs you're running in the data center, we have features of
Yep.
what movies people want to watch. We have all these features, and you want to use sort of more traditional machine learning to maybe do forecasting.
Yeah.
I know you've done theoretical work in this space, but how useful are these predictions in practice?
Really, I mean, they're the key. So in the data center world, we didn't have any of this OBD work. What we were using in the data center world was variations of receding horizon control combined with ideas from online optimization, and the predictions were crucial. And actually, the algorithm design depends on how you do those predictions.
Was there any cases where the predictions were not as good as you'd like them to be?
Yeah, definitely.
And then if the predictions were not as good as you'd like them to be, how much of that hurt performance?
The algorithm would adapt to how good of quality the predictions are, and yeah, and and you estimate it through the evaluation of your performance after the fact.
So there's like a distribution shift where
Yeah.
you're deploying from one data center to a new data center, or a data center A.
Yeah.
The data center B is a little bit different. How do you estimate how good? How do you estimate how good you?
So that's a really good open question. We don't. What we did was the algorithms that we use adapted to the quality of the estimation. And
But how do you estimate the quality?
so through an evaluation after the fact of the quality of the algorithm. So if you think of,
So you just run the algorithm for a while in the new data set, and you tune the algorithm.
and the algorithm self-tunes to how well it's doing and says, oh, I'd put more weight or less weight on these. But that was a hacky, systems deployment of it rather than a theoretical guaranteed approach. Yeah.
So the non-convex setting, I guess that's still a teaser, right?
Yeah, I can send you the paper.
But I'm wondering, even like, how do you define confidence ratio there?
Exactly the same. So the result there says that for as long as there's two conditions on the hitting cost and so what you need is an approximate triangle inequality for the movement cost and an alignment between the hitting cost and the movement cost. And then I don't care about any other properties for the function itself. Still constant competitive ratio in the classical sense.
But it's not with respect to global optimism.
It is.
So you can
Well, that's true. You're hitting on the important point, which is we're assuming that per round you're solving it optimally. So if there's an approximation error in how you're solving it in a per round basis, that ports over to the competitive ratio. So we're separating the hardness coming from online from the hardness from solving the local cost function. Yeah, that's a good point.
But
Yeah.
something like gradient descent for those that where you have some first order.
That's right. That's right. That's right.
Then you have to change.
Then the algorithm, like this would handle the movement issue, and then there would be an error in the bounds that comes from the error in the per round solving of the cost function. We haven't put those two together yet.